Oh, hey, Andrew. Yeah. For some reason, I think the Joshua from CS2A also joined the meeting. Well, I don't. There's no problem with other people joining the meeting, but I didn't want him to be confused.
Oh,
So he was in
okay.
the waiting. Yeah, he was. Did you see him in the waiting room? I mean, can people in the waiting room see each other?
I don't think so. I didn't see anything like that.
Oh, okay. Well, he was in the waiting room, and then he disappeared. So because I wanted to tell him this is what it was, and but anyway, if you happen to run into him in the forums or something, you can let me know.
Oh, okay, gotcha. Oh,
Great,
what
great.
what if I
Okay,
see
well,
him?
I'm glad we managed to connect here. Now you said it was machine learning. It's such a huge area. Yeah, obviously, right? It's a big area.
Yeah.
So what is your interest? So what we can do is I can start teaching you from the very basics, and then we can stop whenever either of us reaches our limit. You can say, well, that's enough for me, or I could say, well, I can't teach you anymore. Yeah,
Ah, okay.
and it could happen as soon as you want. You can say, that's enough anytime. I can do that. I can teach you all the way up to graduate level. Not everything about what I know up to graduate level. Yeah.
Ah, okay.
Uh, yeah. So it all depends on whether it's your cup of tea. But why do you want to measure? Oh, hang on. Yeah, it is recording. Okay, cool. Yeah, right. Because we'll just post it so that if other students, hopefully, other 2A students are also interested, we can say, hey, just watch the video and that Andrew and I made. So
Gotcha.
what is it? Hmm?
I see. Yeah.
Great, great. So what is it that in machine learning that appeals to you? What is it that you want to do in machine learning?
Um. Well, I guess when it comes down to it, I've seen lots of videos from different people that make little sims of like a dude walking around, and it goes through a bunch of different generations until it can figure out how to walk, and it comes up with a bunch of really funny effects that it uses. And sometimes the machine like breaks the physics engine that they're using to simulate the whole thing to accomplish its goal. And I think that whole concept is really cool, and I want to know how you put something like that into effect.
Okay, yeah, well, so what you're talking about is a large part of it is just to do with applied machine learning. Why not machine learning behind the scenes, but really taking the effect of some machine learning engine already provided to you and hooking it into a wireframe or hooking it into, Alexa and hooking into different things to make it do different things. Yeah.
Yeah.
And that itself is a huge field. I mean, there's lots of people, doing research in that area, and it's a huge field, but it's applied machine learning. However, I think even if you go into applied machine learning, it really, really helps to know what's going on behind the scenes. Okay, what is machine learning at the end of the day? We got to know that. So, do you have an
Yeah.
intuition about what machine learning is? What is AI? What is machine learning, and so on? And then we can take it from there. I can explain it in terms that will be so simple you could explain to your kid brother. Yeah,
Mm.
and they would also understand it. And but let me know. So what is it? Um,
Yeah.
yeah. Okay. So do you agree that you want to get some idea, some insight into machine learning behind the scenes? What is it? That people call
Definitely.
machine.
Yeah. Like most likely basics for what you can teach me cuz all I've seen
Yeah. Yeah.
is like stuff of people using it, but I don't know most of the
Also,
in-depth things.
you're right. Most of the videos and everything out there is about how people are using machine learning. And then there are a few courses on machine learning online, I think, and they are actually simple courses, but unfortunately, a lot of people do get turned off because the content of the math content sometimes is high.
Mm.
um, and Math and stats, it is possible to get an intuition of most algorithms without math and stats, but you need math and stat to fine tune the algorithm to do the right thing in the most efficient way. Does it make sense? Just like we've been doing in all of computer science, right? CS2A,
Yeah.
2A, 2B. Because in order to understand how a hash table works, you use CS2A, right? Are you in my 2B, by the way?
Yes, I was in 2A. I'm going into your um 2B
Great,
for
great. Mine's
next
2B.
quarter.
Okay.
Yeah.
So that means you will continue all the way to 2C and hopefully, right?
That's the hope. Yeah.
Great. So in order to understand how a binary tree works or how a hash table works, You don't need a great deal of mathematics, right? Because think about it. Most people who use Python dictionaries, right? They're using a hash table behind the scenes. Yes. They
Yeah.
don't know how it works, and they don't know what the redundancy is and the costs and trade-offs and things like that. They don't know, right? But you can still be a very good hash table user if someone gives you an idea of, this is what a hash table is, use it in this way, and so on and so forth, right? But a lot of people don't even have that intuition about hash tables. But it helps to know what a hash table is before you get into using it. And that is what we try and teach you in CS2 ABC and all these ABC courses.
Okay.
So with machine learning, well, essentially machine learning, in my opinion. Okay, and you can talk to other people. You're in the Silicon Valley, I assume, so you can talk to other people who are in the field. You can get their take on it also. As far as I'm concerned, machine learning is a lab science. It's not a pure science like computer science or math. Okay, computer science or math, you don't need anything that's tangible. You don't need to do anything that's observational, right? You don't need any right, because everything can be done in your mind.
Yeah, definitely.
However, but when it comes to machine learning, you're driven by data. Because you could say, well, here's this incredible theory I have, right? But the data does not agree with it, but you still got to believe it, which is what a lot of people do anyway, right? So there's no evidence, and in fact, you have contrary evidence, and people want you to believe some shit. Yes. So and so the whole idea behind machine learning is how can you make sense of just data points? Because if you look at out there, right, you see lots and lots of data, but as I think by evolution or some way in which our brains are structured, we are looking for structure and ways in which we can minimize the storage of information out there. There's like a shitload of information out there, and we want to try and understand everything. And there's no way we can understand everything. So what are we going to do? We're going to try and make up theories, because it is impossible to remember exactly how the planets behave. So I'll come up with the theory of gravitation. So now I don't need to know exactly where the planets are. I just need to know a bunch of physical laws and some time delta. And given the time delta on these physical laws, I can calculate exactly where each of the planets are going to be at what time.
Yeah.
Right.
Gotcha.
And so I don't need to remember instead of remembering, June 1st, June 2nd, June 3rd, a million data points. If someone asks me what the position is on June 55, now I say there's no June 55, June 3rd, I can just look up the table and say, well, okay, June 3rd, that's where the moon is going to be. All right. Or I could just apply a mathematical equation and say, well, June 3rd, that's where the moon is going to be. Now, which one is easier for humans to remember? Is it easier to remember like a trillion data points or just one curve, one equation like that with one variable?
Yeah. It's
so
the first
that is
one.
what we're trying. Yeah, so and this is what children do all the time. Everybody does. All humans do all the time, and people probably forget it. Is basically to try and look at all these outside data points. There's so many and so much. It is impossible for us to remember all of that. So we try and figure out patterns, and we remember these patterns. And we do this all the time, even with people behavior. Unfortunately, that with that people make huge errors because they cannot look into the minds of other people. Yet they make hypotheses about what's inside the minds of other people, right? So they look at someone and on the street and make a decision about their character when they have no idea what they've been doing for the 45 years before they actually saw them. Right? They could have gone through real shit, and that could be an explanation for what they're doing, right? So people make judgments and just like that. However, we don't have that problem when it comes to the empirical world, because when we look at phenomena out there, many of the stuff that we see lends itself to easy binning into a pattern in our heads, right? So if you're game, what we can try and do is do our 101 exercise today. Right? If you share a screen. Is that okay with you?
Sure.
Yeah? All right. So, by the way, before we get into all of this, are you a Python person, or do you know Python, or we'll do C++, of course. We'll just do C++.
Started with Java.
Okay,
I did.
don't worry.
Well, there was a bunch of different things, but Java was the one I knew the most with, and then we.
Do C++.
Yeah, and then we're going to C++ here. Yeah. Quick question. You mentioned something, a hash table. What is that?
Oh, a hash table is essentially a dictionary. That's all. So, or in Python. No, not Python. Java. Oh, Java. Did you do A, B, and C in Java?
It wasn't.
No, only C has. Only one C has hash tables. If you did 1B up to 1B, you wouldn't have encountered it.
It's not like college classes worth of Java. It was like Java was the one that I got taught in like middle school and high school
Yeah,
for
yeah, yeah.
some
Okay.
activities
Right.
that
So
I did.
no way, no way they would have taught you hash tables, right?
Yeah,
This
so
is all
not like
Java.
not super in depth, just most of the base level things for them.
Anyway, you know about arrays, right? You know arrays. We did arrays in
Yes.
CS2A. Yeah, so in arrays, you have a value that goes into an index, and the indexes are all numbers, right? So if I tell you what is an array cell 47, you'll just look at 47 and tell me what it is. Yes.
Yeah.
Now, what if instead of numbers, I basically had names? I want to have an array called grades, and I have the array grades square bracket Andrew equals this, grade square bracket Nemo equals that, and so on. So I need to have names instead of numbers. Now, all of a sudden, we can't use our mathematical indexing before. With regular arrays, we were basically just able to take the address of the 0th element and then calculate the offset of the nth element, which is basically the size of each element times n. Yeah.
Yeah.
And then we can get there and say, hey, oh, yeah, sharing screen. Yeah. In that case, let me just do gallery or something like that. No, it is actually switched to gallery. Right. So yeah, no, I need to. Can you control plus a couple of times, and then it'll be a new project. Is this Visual Studio or it is VS Code? VS Code.
Is
Yeah.
the Control Plus working?
No, it's not working for me.
Yeah, it's not for
when
me
you do it,
either.
it's not. Okay, maybe it's a setting in VS Code. You can just say, increase font size.
Yeah, give me 1 second, real quick. Yeah, sorry, because for most of the classes for CS2A, I did stuff on my laptop, which was much smaller, but this is my home stuff,
Oh, I see.
quite a
I
bit
see.
bigger. Yeah.
Yeah, I can read it, or I can get my other glasses. But Control Plus should work because the fonts are so tiny here. Why is the font so tiny?
It's I'm trying to change it, but it's not letting me. I hit Control Plus, but it's just changing a little percent thing, and nothing else is moving.
Or you can just change the resolution of the entire monitor.
Oh, there we go. How does that look?
Oh, great. Yeah, that actually you can yeah, I think that's good. That's good. Yeah, it's going to be a brand new project and it'll be empty, so it doesn't matter. And also, we need a Chrome browser tab, and I'm thinking we'll do something cool. Yeah.
Gotcha. I have one open. Do you want it to be like in the share
Yeah,
screen?
just make it and not right now, but eventually, just make it a
Okay.
private window, and then we'll open it up at some point. Yeah.
Gotcha. We can do that. There we go. Okay.
So
New
anyway,
project.
so we're talking about a hash table, and hash table essentially is because we stick in names instead of numbers, we've lost that incredibly useful property that lets us offset directly into the address now. Yes. Because they're names
Yeah.
and strings, they're not numbers anymore. So if I say what is the grade that Nemo got, there's no way I can find out because there's no number associated with Nemo. I got to look up a number or something like that. Yeah. And so a hash table addresses that by giving you what is called an associative array. An associative array is basically just an array, except it associates a string, or it doesn't have to be a string, but I'm saying associates an object, which could be a string, with a value, and which could be anything you want, like an array of pets. And Nemo owns this pet. Jordan owns that pet, and Andrew owns this pet, right? So you can have an array of pets, but it's all indexed by name. Now, how do you get to the correct cell efficiently if it's all by name? One way is you could just do a linear search like you do in quest number 7. You start at the first element and basically just keep looking, Andrew. Yeah, all right, found Andrew and get the pet. Yeah, that's one way to do it. Yes?
Yeah.
All right, this is a painful way, isn't it?
Yeah.
All right, so a slightly better way is always maintain the array in sorted order. So you can do a binary search.
Yeah, gotcha.
Like a dictionary. Even that is also painful. If you think about it, first of all, you got the added overhead of maintaining it always sorted. And as a random element comes in and you got to insert it, you got to do a whole bunch of shuffling around, put it in the right place. It's a real pain in the ass, right? To maintain a sorted array.
Yeah.
But if someone gives you a sorted array, the efficiency of getting to an element is not constant time like that. You got to, like binary search, you got to divide in half and then divide in half and divide in half. And you got, it's logarithmic. It doesn't go, it's log n time, right? The number, if the size of the array gets cut in log base 2, right? It just keeps getting shorter and shorter, but you still got to search.
Yeah.
So we want to find the array and the element you want in constant time. What you do is you have a clever function that takes a name and converts the name into a number. That's all. Okay. And then that number is the index into the array. That is a hash table. I'm not going to go into the details because that's irrelevant to machine learning. Yeah.
Gotcha.
But I'm saying you just need to know about machine learning, array hash tables before you. Then after you say this is the fundamental, principles behind an hash table, then you can start looking at, well, if I do that calculation, what are the ways in which it can go wrong? We're not going to go into any of that. We do that in CS2C. What are the ways in which it could go wrong? What happens if I just keep doing calculations and end up in the same place instead of new places? All those things, right? And then you bring in mathematical insight and say, well, we'll do the hash table in this way so that this kind of thing doesn't happen. So that's where you need all the specialized stuff. Same thing with machine learning, right? So in machine learning, what happens is that if I gave you a curve, a bunch of points that basically satisfy the equation, we'll just pick a. Actually, yeah, go to Chrome, the private window, and just go to desmos.com. Been wanting to try this out for a long time, so we can see desmos.com. Desmos.
Gotcha. Do you share it? Hold up. Did that switch to the window?
Yeah. I think I'm looking at desmos.com.
The keys. What are
DESMOS. DESMOS.com. All right. So graph visualization software. So let's draw a parabola, very simple parabola. Wow, what they changed these? They changed all these interfaces. Yeah, I think it's the second one, view website or something like that. Graph.
This one?
Yeah, I think no, it's a toolkit.
Oh.
No, we don't want a toolkit. Visit website. Well, what the hell happened here? Just go to Google and type draw graph in Desmos. Just go to Google and type draw. Yeah, right in the URL bar. Draw graph in Desmos. All right. Okay. All right. So that's where we wanted to go. So what is the end URL here? Desmos.com/something. I can't read that. I think it's just graph calculator.
Yeah.
Is it calculator?
Yes.
Wow. I wonder why.
I can try and. Well, that doesn't help the top, but
it doesn't help. Yeah, it doesn't matter. Yeah, we can put it back to regular size. Let's just draw a random parabola here. Let's say 3x squared plus 9x, y equals 3x squared plus 7x, right? Let's just pick some prime numbers here. 3x squared plus 7x. Now, it should be a parabola, not a line. No. Oh, yeah. Okay. All right. Good. Yeah, that's good. That's good. No offset. No. Do you add something there? Why is it gone down? It should be 3x squared plus 7x. That's funny. Why? Oh, wait a second.
Oh.
When x equals 0, y should be 0, shouldn't it? Oh, it is. Yeah. Why the hell? Well, I mean, maybe I've forgotten some basic mathematics here. Okay, no, that looks right. All right. Okay, so let's just have this parabola, and any old parabola will do. Yeah.
Gotcha.
All right.
Make it.
So now, suppose I gave you some points. You know what? Actually, let's just pick a very simple parabola. X equals, y equals 7x squared. That'll give us a regular looking parabola.
Gotcha.
7. Oh, x squared by 7 or something. X squared over 7. X squared over 7. X squared over 10. Right. I think x squared over 10 will be flat. Yeah. All right. Good.
Yeah.
I think that looks good. All right. So if you zoom in and I give you if I give you a bunch of points, right? 0, 0. Actually, go on the next line. Hit enter. Try it. This is what I wanted to try for a long time. Within parentheses, we want to specify a single point, right? Say 0, 0, and we'll see what happens. Yeah, enter. No, close. Yeah, enter. Did it do it? Oh, it did. It did actually put a dot there. Oh, that's really cool. Yeah. So I think what we can do is So that's great because in our C++ we can actually go and generate a bunch of points and copy and paste in here, and we'll just scatter a lot of points in there. Yeah. I think that'll be cool. All right. So suppose I gave you some points, right? 0, 0, 1, 1. I don't know all the points that lie on the parabola only. Yeah. So now let's go to our C++ program and generate them, right? So what was it? Y equals? Oh, it's just y equals x squared. Yeah, okay. Let's just do y equals x squared. Okay. So let's go to our C++ program and let's write a very, very small C++ program. And by the way, you got to tell me how how you're doing on time. Okay. If you want me to hurry up and speed up, no problems. Okay, I can any pace that you want. I can do
Oh,
it.
okay. I only have to do things along come like 6, so I have a bunch of
Yeah.
time.
All right. Okay. Cool. All right. I can keep talking and until I get tired and then take a break and come back to. I don't have a problem. Okay. Yeah. Create a new project altogether. New project itself. In fact, you're gonna just go to online GDB on another tab there, right? Because it'll save us the time to switch between Chrome and VS Code. Just go to that
okay.
Chrome window. Just go to online GDB in another tab, and we'll do it there.
Gotcha. Give me a second.
No worries.
Okay, there we go.
Yeah. So just go to onlinegdb.com.
Is the screen shared?
Oh yeah. I can see it. Thank you. All right. Yeah.
Alright, cool.
That's great. So just create a simple loop there. For loop from 1 to 10, and print numbers 1 on each line, and say, all right. Let's just loop first. Yeah. I equals 0, I less than 10, I plus plus. Yeah. So on the next line, you say cout, left shift, and then open parentheses, within quotes, open parentheses. Yeah. And then, no, just open, not close. Yeah, there you go.
Okay.
Now left shift I.
So that.
And then comma, and then I squared. I star I.
Oh, so
We want to print that point.
comma and then
I star I. And you may need to put I star I within parentheses by itself because of precedence rules, I think. I don't know.
gotcha.
And then I've sticking an endl at the end. All right. Now let's run this and then copy those points and see what we get.
Okay.
Just run it. Okay. All right. So now you see those points? Now copy those points and take them to Desmos and put them in there, and let's see if it actually puts dots on all those places.
I could say.
It's not even pasting?
It is not. Let me try one more time. Control C does not seem to be working.
Probably. Oh, can you right click and paste? Right click and select paste. Maybe they trapped Control V.
Let me see. Copy.
Oh, there's no paste enabled? No enabled. The paste is not even enabled there. Also, they cut the entire menu. They took over the entire menu then. Wow.
Well.
Yeah. Well, okay. I guess it's
like this.
It's okay. You don't have to do everything. I just thought it'll be nice, but it's not. It'll waste a lot of time. Suppose I give you those points, okay, and you plot them here, and get rid of that, red curve. You get rid of that curve at the top. Yeah. Now you see if you plotted them and you look at this, and what would most people do? They'd say, well, you know what? That looks like a parabola. Yes, because because there's no error. There's absolutely no error. Yes.
Yes.
Because we have I and then I squared. For every I, we have an I squared. There's absolutely no error.
Yeah.
So then if you plot the points, it looks very nice, and you can make these really cool theories. Yeah. And so if I give you 1,000,000 points like that, and ask you to store them, most people would basically say, wow, what a pain. I don't want to do that. It's 1,000,000 points. I don't have to. But there's a clever way to do it. You can say, I don't have to store the 1,000,000 points. I just store the equation y equals x squared. That's 10 bytes. Yeah, someone says, what was, give me the point for 75. All you have to say, 75 comma 75 squared, because you got the equation. Right. Okay. So now, how did you come up with the equation? Because I just gave you those points. How did you come up with the equation?
The equation y is equal to x squared from the points.
Yeah, but suppose I just gave you the points and I never give you the equation, right? And by looking at the points, because in the points are just points, there's nothing between
Yeah.
the points. Yeah. So but you came up with the equation and it seems to fit perfectly. Everything looks, hunky-dory there.
Yeah.
So something has happened.
The
Something, yeah. So do you agree that something mysterious has happened there? Because from a
Yes.
scientific point of view, from the point of view of true science, some mystery has happened here because we just made a jump, which is unsubstantiated. You're not evidenced by science. We just said, well, you give me 1,000,000 points, but I can give you an infinite number of points because the curve y equals x squared is a continuous curve. It's not a discrete, set of points.
Okay.
And we know that a continuum has uncountably more points than any series, even an infinite series of dots. That's a beautiful theory, isn't it? It's not a theory. It's a beautiful fact. You can prove it. I don't know if you're interested in these things, but the integers, right? Integers, you have an infinite number of integers, right? 0 all the way to infinity.
Yeah.
But still, they're just called integers on the lattice point, which means that the number line has a lot of holes because the integers only happen to occupy these lattice point 1, 2, 3. In between 1 and 2, there's nothing in there. Yeah.
Yeah.
So if you want to fill up the gaps, then you got to resort to the continuum, right? That's a continuum between the points. That's a continuum.
Yeah.
And we can actually prove mathematically that even though there's an infinite number of integers, there's more numbers just between any 2 points on the continuum than all of the integers put together. Right? So even if you take two really close points on the continuum between 1 and 2, right? 1 and 0.0001, right? That small line there, that segment, even that segment has got more points than, but it's all right, you're yawning. But anyway, so you gotta tell me if I'm boring, okay?
Not because of that.
Cut the fluff off.
I didn't get the best sleep last night. Sorry.
Okay, but you got to tell me if I'm boring, okay? So I can just switch gears at any point because you said a lot of time.
Just asking to know if I get what you're trying to get at here. Are you trying to talk about the whole fact that machine learning is the concept of like figuring out what something is based off of comparing it to like prior data, so that it can make
and making a wild ass guess about what could exist between the places where we haven't seen. Yeah, because otherwise there's two kinds, and people usually say this is also machine learning. That the other thing is not machine learning. It's called memory-based learning. You encounter the term when you do machine learning, something called memory-based learning, MBL, right? I think so. I think that's what it's called. Memory-based learning does not do any machine learning. It'll just take all the data points and store them internally, right? And someone says, what is it for, value 75? It'll look it up and give the answer, right? It'll look like machine learning because it's got a shitload of points in there, but it's really memory-based, right? But machine learning means I'm going to now say, I'm going to deduce an equation like Sherlock Holmes, okay? And that's what I'm going to remember. I'm not going to remember. So that step is what machine learning is. And all of your tenure in machine learning, you're just going to be looking at ways in which you can infer what you cannot see. Now, the gotcha there is that any time you infer something that you cannot see, there's always a slim possibility you could be wrong. Yes. For example, I could give you all these points that look like a perfect parabola, yeah, but in between it may not follow a parabola, right? It could just be a glitch in some kind of a warp a wrinkle in space-time on the event horizon. Yeah, it's that slice that projects into our dimensions is all the points of the parabola, but it could be all kinds of crazy things could happen inside, right? So it's all possible. So how do we make sure that we get the theory that has got the greatest chance of being right? Yeah. So now that's what we're going to try and do. So, and this is machine learning 101, and this is what every ML student is taught when they start is called. It's called the Occam's razor principle. Every culture, every civilization known to man, they have different name for this. It is what every child does. Occam's razor is that if you have a bunch of data points, yeah.
I've heard of that, yeah.
If you want to come up with a theory, there's many theories. Someone could say, the theory is that these are the the individual data points are the theory. There's, you know, there is no theory. There's not a continuous theory, right? The data points are theory. The other, someone else could say it is actually a parabola. It's a very close and succinct theory, right? Someone else could say, you know, more complex curve, but actually intersects with every one of the data points. So there's many theories that could explain the same data, right? Just like you have observations and many different scientific theories that explain the same observation. You know, if you take planetary motion, you have the Copernican theory, the heliocentric theory, everything tries to explain this, right? And general theory of relativity, that is also trying to explain. And because what happens is that we try and fit a theory to our observation, but because it is nature and real, a lot of the observation that we see does not fit with the theory. So what happens is that the points that you get are not exactly on the parabola, but there's noise around the points. So you don't have 0, 0 and 1, 1, but you have 0.001, 0, and then 1, 1.2 sometimes. Instead of you know, what is it, 2, 4, you might have 2, 7. Yeah, because it will be a huge error. Given a lot of points. Now that is a challenge. Okay. Now that is what science is. That is what empirical science, lab science is. You get lots of data points. We got to look at the data points and get a solid intuition for what constitutes noise in that domain. Okay, not general purpose noise. But you know, we generally luck out because most of the noise is Gaussian. Gaussian meaning it is normally distributed, so it has some very nice mathematical properties. So we can say, you know, we can model for this and say we want to minimize the error, which is what we're going to try and do, right? So if you go to our C++ program now, right now, where we want to say inside the for loop, you say change that to int x equals 0 to make the variable I will leave it as I for now, and I. And then inside your braces, before the cout, you can do say double fx equals double space fx equals I times I. What we want to do is inject some noise into each, and let's make the noise Gaussian. All right, so now what we want to do is plus I star I plus I star I space plus.
Yeah.
I don't actually, there's a lag. I don't see.
Plus?
There you go.
You don't see it?
Now I yeah, now I see it. Okay, plus we're going to generate noise, noise, noise. Noise, and then open close, right? Okay. And then let's create a noise function up there above main. Yeah, and I say double noise, right? Open close, and then braces. Put the braces. Yeah. Okay. Now above the noise function, let's put some comments so that it's very clear what we're doing. Right? To say generate a Gaussian number between -5 and -0.5 and +0.5. Yeah. Well, you know, yeah, actually -0.5 and +0.5. I think that's okay. All right. How do we do that? How do we generate Gaussian? Let's say we generate three elements. Okay, all right. So yeah, so inside your hit enter one more time. Yeah. Now what we want to do is say double rand1 equals say rand open close rand divided by rand max
is this going to be a
uppercase divide, no, not
constant?
percent, divided by
oh, okay,
divided by rand
constant?
max. Why is it not maybe it's max rand, maybe max rand. No, uppercase max.
Oh, okay.
No, didn't do it. No, it did not complete. I think it's rand max. It's rand max. And then Oh, maybe the include file is missing. So let's just include hash include hash include std lib.h, hash include std lib.h. Yeah. Now I think rand underscore max, by the way.
Okay. Huh.
No, I don't think it. Yeah, but I think it'll work. Okay. Now semicolon there. Oh, semicolon, and then typecast the rand into double. So you want to put double within parentheses right before the rand. Yeah.
Gotcha.
Yeah. Right. And put a space after the typecast so that it doesn't run into the word rand. Okay, cool. Now you want to copy this whole line and paste it 3 times. Paste it 3 times.
Okay. Just like going down.
Yeah, right. And then you know what? We can do better than that. Just put in a yeah. All right. So we can actually do better than that. I'm sorry. We'll just refactor that. Just do a for loop. So you say for size t I equals 0, I less than 5 maybe. Yeah, I less than 5. I plus plus. And then you want to say double total plus equals, and then whatever you have on the right side of that, right? So yeah, double total, change rand1 to tot, T-O-T, but total, T-O-T-A-L, and then change the equals to plus equals. Yeah, and then above the for loop, initialize total to 0. Yeah, declare and initialize to 0. Right, enter, blank line after the declarations.
Gotcha.
Yeah, all right, so now, so total, now that would have 5 randoms added to it. We ran into an issue last time. Just give me 2 seconds. We ran into an issue in class in CS2A because rand on online GDB returned a huge number. Not rand max was, was small before. And then it's caused an overflow and didn't give us a Gaussian. And then Walter did an experiment. And then he said, well, this is the reason. Yeah, okay, I remember that. Okay, all right. No, so here's what we want to do. Rand. All right, so instead of rand, say my rand. Okay, instead of say rand, say my rand, my underscore rand, and we'll define our own my rand. Okay, right?
Okay.
And then go above, yeah. And then we'll complete this function and go there, right? So outside the for loop, you just want to say return total divided by 5 minus return total divided by 5. No, we want the word return.
Oh, gotcha. Sorry.
In fact, you can put a blank line before return too, because it's the final paragraph. Yeah. Right. So return total divided by 5. Because I goes from 0 to 5. So it's 5 randoms added to each other, and each random will be I don't know, let's say between 0 and we'll generate each random between 0 and 1,000. Okay. So 5 of those the average will be 5. The average will be about 2,500. So yeah. So all right. Okay. This is what we'll do. All right. So we'll do that function for myrand, and then we'll come back to you. We'll change the name of myrand to myrand underscore 1000. Just myrand underscore 1000. Yeah. For now. We can clean up all of these later, right? When you refactor, because we're doing this half-assed shit here because we just want to go for the concept as quickly as possible. Now let's go above this function. Yeah, let's go above the function and just now above and declare our myrand 1000 function, myrand 1000. And that's got to return a double. And we can say actually the no, not double. You can return just an int. Yeah, and then this can return rand percent of 1000. And this could potentially just be inline. You can just do everything and put the same thing on one line. Yes, one line. Yeah, you can say curly brace, return rand percent 1000. Return rand, open close, and then percent 1000, and then stick the word inline, INLINE, right at the beginning, right at the beginning.
In line?
No, not there, not there, not there, not there, not there. Before the. Oh yeah,
Oh,
yeah, there you go.
in comments?
No, no, no. In front of the word int, right? In front of the word int, say inline. What that means is that you can get rid of the blank line above that, and then you're missing a space before the curly brace too. You can fix that. What inline does is that it's a hint to the compiler saying even though it's a separate function call, don't call it like a regular function where you have to take the return address, push it on stack, and actually call it and use a call statement. There's a lot of overhead in a real function call. You stick the word inline, it tells the compiler, right? Make it look like a function call, but it's really not a function call. Wherever you see that function being called, take the actual code for the function and put it there. So instead of us typing the code there, we can put it like that.
Oh, to just make the whole thing like smaller?
No, it's to make it more efficient. Because if we didn't do that, well, technically today's compilers will automatically inline it, whether you tell it or not, because it's so simple that that logic can be inline. But in the habit comes from back in the day when you have code in a for loop, you have code in a function, right? So you have code in a function, but the for loop is going to be iterating 5 million times, and you don't want the function to be called 5 million times, because every time you call a function, it's a stack overhead. It's a stack, isn't it? You got to push the return address, call the function. After the function is done, it's got to pop the return address and go back. So this is loop, and that is that function call is expensive. So we want to say we want to get rid of. So that is why when you write high performance code in C++, you'll try and minimize function calls and say, instead of calling a function, I'm going to take whatever the function does, the 10 lines of code, and plop them right there. 10 lines of code instead of the function call. That'll be a whole lot faster than calling the function.
Okay.
That is called inlining the function. That is called inlining the function. Now the compiler can do that for you if you just say inline in front of it. Okay, so and your code will be faster, but we don't have to do that. We're just saying this is just good practice. Yeah. All right. Now here in our function, it's going to call myrand 1000. So it's going to get a total that could go all the way up to 5,000. You're going to divide by 5. So total divide by 5 will be between 0 and 500. What is it? Between 0 and 500?
Between 0 and 500.
Oh no! Hang on. Oh yeah, total. We can actually just do this. Okay, we can do this. Yeah. But total divided by 5,000. Total divided by 5,000. Total divided by 5,000. Yeah. Gotcha. Now that should give us a number between 0 and 1. Yes or no? If you just divide by 5,000, because each rand call will generate a number between 0 and 1,000. You're going to add up 5. How many? 5 of those?
Oh yeah.
Each one is between 0 and 1,000, right? Each call is going to give you a number between 0 and 1,000. You add up 5 of those, the sum is going to be between 0 and 5,000.
Okay.
No,
okay,
don't
yeah.
say okay.
No, sorry, I was just having to think about it a little bit. I'm not, I wasn't fully following what was going on with the rants, but I think I do a little bit more now.
Let's take time. Yeah, let's take time, understand this, and then move on. Okay. So what we're doing here is essentially in our for loop inside of where's that for loop?
I got it now. Yeah.
You got it now?
Yeah. It just took me like a minute or so. Also, rand max, we haven't defined that as anything, and I don't think it knows what it is either.
Oh no! We don't need rand max anymore. Just get rid of it. Yeah, we don't need that. Okay. We don't need that because now double myrand 1000. And myrand 1000 inline it returns in it. Okay, yeah, all right. So that's good. So that's going to return a number between 0 and 1,000. And then we're going to add 5 of those and get 0 to 5,000, divide by 5,000, right? Now, however, we want so that is going to be between 0 and that total divided by 5,000 is going to give us a number between 0 and 1.
Yeah.
So here's what we're going to do. We're going to take that number from 0 to 1, subtract 0.5 from it. What will it do? What will it do? If you take the number between 0 and 1 and subtract 0.5, what do you get?
Something that is between negative 0.5 and positive 5.
Yes, exactly. So now return that. So now return total, divide by 5,000 minus 0.5. Okay, good. So that is our noise. what that means is that it's just going to give you a random number between 0 and 0.5, between negative 0.5 and plus 0.5, and you're going to add it to the y value that you calculate here. Okay, so in our for loop in main, in our for loop, yeah, so you say fx, yeah, there you go. We'll already do that. So I star I plus noise. Now we don't get perfect squares. We get for x equals 0, you get some some number that is slightly offset. This is slightly offset. Okay. Now if you join them up, you won't see a perfect parabola. You'll see like a jiggly set of lines. Yes.
Yeah.
Hey, run it. If you run it, you'll see the points are slightly off center now. Yeah.
Yes.
What is it?
You had an error.
No. Right. What does it say?
Equals.
Double total plus equals. Oh yeah. I'm sorry. Yeah, good. Just get rid of the word double. Just get rid of the word double from. But
oh yeah, because we did it twice. Yeah. I didn't think of that.
No. Yeah. Now, you run it now, and we'll see the numbers. Yeah. Ooh. Okay. There you see. Right now, if you take these numbers and plot it in your Desmos, and that's the bit that I don't know how to do. Hang on. Can you actually? How do you get these numbers into Desmos? Yeah, I wanted to try that. I should have tried that before, so I could have figured out an alternative. But if you can think of a way to get it into Desmos, that's great. Otherwise, you have to use your mind, poor man's Desmos, and say, well, that's what it's going to look like.
Control C doesn't work. That's really weird.
Can you paste into text edit or anything at all? Anything at all? Oh,
no, that was from earlier.
No, but still,
that was from a different thing
from the clipboard. Yeah.
I can do that, but it's just not letting me take out of here.
Take that and put it into Notepad or something. We'll see if it at least goes into Notepad.
Wait, what if? There we go.
Oh wow. Okay. No. Yeah. I think so. It do it. I can see the points. No. Shrink. Zoom more. Zoom.
Oh, it did.
Yeah.
It had the commas and everything.
Points. Now you know what? It's the jiggling is not. It's not perfect, but we want to increase the noise. So go back to that.
You can do this. You can see it. How it's
yeah. In fact, if you can point. Yeah. That's right. Yeah. Now, if you can plot the curve, you can see that many of these points are slightly off center, right?
Yeah.
Okay, now that's with very little noise. We just inserted very little noise. And look at the noise is actually not even a function of x, right? We're just inserting constant noise. Now, the challenge is to come up with a curve for the parabola, even when you have lots of noise.
Yeah.
So how do we do that? So this is the first project in machine learning for my grad students anyway. This was the first project, and it's very easy. And we basically just use something like Occam's razor, which we say we have lots and lots of theories, right? The theory that we accept is a theory that is most easily able to be remembered and stored by me in my memory. That's essentially what it boils down to. Meaning that I can have an absolutely simple theory, right? My theory could be so simple that I don't have any theory at all. The points are the truth. I don't have anything other than the points themselves are truth. That is my theory, right? I don't have any explanation for what happens between. But if you want the value at these points, I can give it to you. That is my theory, right? But if that is my theory, then I got to store a lot of data in my head for the individual points, right? Because if someone asks me what is the value for x equals 5, I need to look it up and give it to them, right? I need to have every one of those data points in my head. So I need to store a lot of data, but I don't have to store any theory at all. Because my theory says theory is a null theory. No theory, just look at the points. That is my theory. That is called a null theory. And even in empirical observations and space observations, galactic observations, you can have a null theory that says I don't have an explanation. What you see is what you get, right? So no theory at all. That means that everything you see is part of your theory, really, because if anyone asks what needs to happen, there you need to see the actual thing. Otherwise, you can't get it, right? No theory. However, you can go the other extreme and say I'm going to have a theory that actually predicts everything, right? So such a simple thing. Right? I don't have to store any data points at all. Now, in that case, my theory will be so complicated and the data storage will be very little. Because my theory, so if it was a simple theory like a parabola, right? My theory can also be compact. But imagine if I had a lot of noise, right? And points were all shifted. And I still want a perfect curve that actually touches all the points, not just go between, touches all the points. Then my curve is not a simple parabola, but it's got to be like a warped curve, like this, touch all the points and go. Yes.
Yeah.
Now, if that is my theory, I can store it simply like y equals x squared. It's going to have like a trillion coefficients. If you describe the curve mathematically, because it's like a warped curve, I need a very, very complex equation. Very complex equation, right? Many powers of x, and many powers of x, and so lots of coefficients. And so my theory takes a lot of space to encode, to remember in my head, but I don't have to remember any data points after that. Because someone tells me what it is, I can still apply the theory and get it. But my theory, so what is the best theory then, right? So we have two ends. One, the theory is so complex and you don't have to store any data because it explains everything. The other end, the theory is actually very simple. It says, no, I don't know anything, but you got to store a lot of data. So you got these two extremes. Now, that is the fundamental intuition between all of machine learning. If you understand that, you go to grad school, you're already at a started a running start. Okay, so the fundamental understanding there is that these are the two extremes, and machine learning is to try and find a theory between these two extremes. In one where there's no data, and the theory tells you everything, and the other where there is no theory at all, and the data only tells you everything. Right? So somewhere in between, you got to find a sweet spot that says, here's a theory, right, that has some data that is not explained, but it explains a lot of data. So there's some error. So how do we pick that? So one way in which statisticians, mathematicians over the ages have found is to say, all right, we'll pick the theory that will have some data error, but then we're going to try and minimize the errors. Okay, that's all we're going to do. So we're just going to say, we'll find a theory that is as compact as possible, while at the same time, the data does not have to be stored like that. We'll just store the errors, the offsets from what the theory predicts. And if the theory is good, the offsets from the actual theory won't be a large amount. So I can store them really succinctly and small.
Okay.
That doesn't make sense.
Yeah.
Yeah, because these concepts, once they sink in, it'll take a little time, but once they sink in, it's like solid, right? Because it's like bedrock foundation for machine learning.
Okay.
We just want to identify the sweet spot theory.
You're saying your system would look for what line looks like it would fit it the best, and then it would check what the percent error from point to point is, and if it's small enough, then it'll say that that's right.
Yes. Yes.
Oh, okay.
But and obviously, and then you can say, well, someone else could say, with my theory, you can get an even smaller error, and you can always say, you can compare, right? Yeah, okay, we can get a smaller error with your theory, but this one is easier to represent and remember. So I'll stick with this, even though it's got larger error. It's easier to remember. It's simpler, and so you can make these trade-offs. Yes, that is what science is. Science is all about trade-offs and adjusting things for the real world.
Okay. How would you make something? How would you make something that could find the line in the first place? Because what you said is how to make sure it's the right line, but how do we teach it how to get close to that line?
Yes, fantastic. That's a great question. And in fact, we should have started with the line. I don't know why we started the parabola, right? Because a linear equation is linear regression is what they teach you in statistics, right? Initially. So I think I started with the parabola because I was thinking, well, it's a curve, and then we can go to gradient descent and things like that, which eventually you'll get into, right? But the line is just as good, right? So you got this line, but the points are not on the line, but there's these offsets. What we want to do is essentially just calculate the error, the total error of all of the data points, all of it, because any point that is on the line, the error is zero right there. Yes or no? If the point is on the line, the error is zero.
Yeah.
Right? But if it is off the line, then there's a perpendicular distance between the point and the line. And that perpendicular distance is the error in the hypothesis. Because your hypothesis predicts a line, but the actual data point is off the line. So the error is that much.
Okay.
No, not okay. Just say a bit more time, okay? I don't care. You say hang on is fine, but okay is not good, because okay says you're accepting what I say. Yeah, so you just need a bit more time. Just say, that's fine.
Meant that as more of a yes. Sorry.
Oh, I see. Okay. Yeah. I'm saying okay too. Guys, I'm sorry. I should be preaching here. All right. So,
It's all good.
so essentially, what's going on is that you're just calculating the error of each point and then adding them all up. Now, if you have 1,000,000 points, okay, each one will have a little bit of an error, and you get the total error. Yeah.
Okay.
And we
So
want to minimize it.
the one we're doing next is just calculating the error from each of the points to the line, or
Yeah. Hang on. So but how do you know it's a line? How do you know it's a line, right?
yes,
So
that's
yeah.
the part I wanna figure out how we figure out what type of line it is. Yes.
Right. Basically, you're asking what degree of the polynomial it is. Assuming it's one variable, you want to say what degree polynomial it is, right? Or even it's a polynomial even, right? It could be an exponential curve, which is not polynomial. Yes?
Yeah.
E to the x is not polynomial. However, strictly speaking, e to the x can be reduced to a polynomial with an infinite number of terms. Yes or no? Because e to the x is basically just a sum of 1 plus x squared over 2 factorial and so on. Yes?
Yeah.
It is expansion.
Yes.
So technically,
yeah, all that. We did that for a bit in math.
Yeah. So any trigonometric function, any continuous function, right? So you just use Taylor's expansion. You can and I think maybe not. Well, at least for trigonometric and exponential functions, you reduce them to sums of polynomials. So you can have a polynomial that's got an infinite number of terms.
Yeah.
Right. And so why did we get started talking about that? Yeah. So how do we know? How do we know it is this kind of polynomial? Yeah, that's right. How do you know if it's a line or a parabola or a cubic or basically exponential with an infinite number of terms? We don't know. Yes. So that is where a lot of and the same thing that scientists would ask, right? When you see an apple fall down, and Newton saw the apple fall down so many times, right? Why did he say that? Why did he form the equation that half at squared, t squared? It's not linear in time. It is accelerating downwards. Yeah.
Yeah.
So it's parabolic. So how did he come up with that parabola? He didn't apply machine learning. So he just looked at the data and said, well, it seems to follow a parabolic trend. So I'm going to assume that it's a parabola. So you look at the data first and say, I'm going to assume it's linear. I'm going to assume it's a parabola. I'm going to assume it's exponential. And you can do all that in Microsoft Excel, right? You actually throw a bunch of points at it, Microsoft Excel or Google spreadsheet, and you can actually select the points and say fit a line to it or fit a polynomial to it. And it'll do that in the background. And all it's doing essentially is taking the error, taking the sum of the error. Every point has error. So you add up all of the errors, you get the total error. Yes?
Yeah.
But the mean error is what you're interested in. Because, if you have 1,000,000 points, your error will be, a millionfold what it'll be 1 point. So what you want to do is add up all the errors and divide by the number of data points. So you get the mean error per data point.
Okay.
Yeah.
Yeah.
Right. Once you got the mean error per data point, you can say, well, now I've got the mean error per data point. I want to minimize that error. And that mean error per data point, there's a number of techniques. We'll go into some techniques maybe later. Maybe I should set up a small, maybe I'll set up a small task that actually has you minimizing the error. But essentially what we're trying to do, so by the way, before I said, some of the errors are positive and some of the errors are negative. Yes or no?
Yes.
Right. So if you add up all these errors, what can you expect to get? Million times, right? A million of those. You add them all up. What can you expect to get?
Well, you don't know how many of them are going to be positive versus negative, but I guess still something that's not going to get very large, because some of them will still be negative.
Yeah, because they're going to be distributed on both sides of zero equally. You can expect that 500,000 will be positive and 500,000 will be negative on average.
Yeah.
And they'll also roughly cancel each other out.
Yeah.
So the sum in the limit will actually be zero. So if you have lots and lots of data points with the same kind of error, they'll all get canceled out in the end. If you sum up infinite numbers of them and say the total error is zero. Guys, does that mean that theory is perfect? No, it's riddled with errors. Every point is this side and that side. Nothing is falling on the line. right? But you still add up all the errors and say the errors. So we do. So that's because we're adding positive and negative values without discriminating between them. All we need to do is make sure that the error is always additive. You know, more points you add, the more error you get. There's two ways to do it. You can just add up all the absolute values, because whether it's 2.5 over or 2.5 under, it doesn't matter. The error is 2.5. So you can say I'm going to take the absolute values and add them all up and minimize that.
Okay. Wait, so you're saying we could figure out what the line is from a set of data by calculating the error that each point has to the line, and if when you add up that error, it roughly gets super close to 0, then you can tell if it's that line?
We want, all right, so here's, before we say we're going to infer a line, we got to make up our minds that it is in fact a line. We got to say, I want an equation.
One of those, yeah.
From these data points, infer for me an equation of the form y equals ax plus b.
Yeah, that's what I said line, but I did mean curve or just equation of some type.
Yeah. And so all we're going to try and do is that, all right, so in order, you want y equals ax plus b, but all these data points are this side and that side. I'm going to add up all the errors. If all of the points are right on my final equation that I'm going to give to you is y equals 3x plus 7. That's what I inferred. Yeah, so maybe I'll come up with that and give it to you. But however, each of the points you gave me are on this side and that side. They're not actually on 3x plus 7. Right? They're on this side and that side, they're distributed, so each one has error, but my 3x plus 7 is a line that actually minimizes those distances, right? When you add them all up, you get the smallest possible number.
Yeah.
Right? So you can do that by adding up all the absolute values. Technically, right? You do it by adding all the absolute values of the errors, because whether the number is off by this side or that side, it's still an error. I'm going to add up all the errors. So take the absolute value of the error, add them all up. I want to minimize that quantity.
I guess.
Absolute mean error, not total absolute error. Absolute mean error.
Oh, okay. Yeah. Gotcha.
Right.
Yes.
So, however, the problem that is perfectly fine. Okay, if we're able to do that, we should do that. However, there's a problem using absolute values. If you think of the curve for the absolute y equals absolute x, right? It's not a continuous curve. It's a V-shaped curve. It goes like that at 0 and it goes like that. So at V, at 0, it's not you can't differentiate it at that point.
Yeah.
Yeah. So it's a pain. So what we want to do is, instead of using absolute values, is there another way in which we can make sure that the errors are positive? Errors are always non-negative, right? Errors are always non-negative.
Square them, I guess.
Yes. Great. See, most of these concepts, these are machine learning concepts, and I'm not coming up with them, right? I'm explaining the problem to you, and you're coming up with these solutions, right? Okay, so all you need to do now is basically just add the squares of the errors instead of the absolute values. But because y equals x squared is actually a parabola, not a V-shaped curve, it has this important and interesting property that you can differentiate it anywhere.
Yes.
Yeah. So if you take the squared errors and add them all up together, and then divide by the number of data points, you get the average, the mean squared error. Yes, the mean of the squared errors, the mean of the total of all the squared errors.
Oh yeah.
Yeah, that is called the mean squared error approach, MSE. Right?
Yes. Gotcha.
That's all it is, right? It's MSE, and what we want to do is we want to come up with a theory in which the MSE is as low as possible, and if you're lucky and your theory is good, you'll actually have a theory that for which all the data points very close to the actual curve, and your mean squared error is very low. Now, so because it's a continuous curve, now the error is now a continuous curve, isn't it? Yeah, because it's continuous now, we can differentiate it. And we can apply these interesting things. We won't do this now, but maybe we'll do it next time we meet, or you can try it on. Yeah, actually, you should try it on your own. And next time we meet, we can say, hey, I played with this, and this is something I found. Is basically trying to do something like gradient descent, right? So if you have an error, right? If and let's say your error is like a parabola, right? So all these parameters change, and as you change the parameters, the error keeps going down, or maybe one parameter, right? And at some point it is very low, and then you keep increasing more and more, so the error also increases. So this is the point we want. The lowest error point is what we want to discover, and you can do that by taking an arbitrary point on the error surface. In this case, it's a line, right? And you say, well, what is the slope at this point, right? The slope. If the slope is positive, so I want to go to the left. So increase, decrease the value of your parameter x by a little bit, right? Test again from the theory and the data point. Test again from a data, and then you can say this technique is called gradient descent, because at every point on the error surface, the error curve, because if you have only one variable, you're looking at an error curve, right? But if you have many variables, you're actually looking at a manifold, a multi-dimensional surface. It's exactly the same, right? People think, machine learning and math deals with infinite dimensions and infinite, hyper-dimensional surfaces. What did I say? Manifolds and all. Nothing, right? It's basically just if you can imagine this happening in one dimension, it's exactly the same, except that but you can imagine how much more complicated the surface will be now, because it's like you have this surface. And you take a ball, right? A paper ball, and it's crumple it, and it's lots and lots of little crumples everywhere. It's not a perfect sphere anymore, right?
Yes.
Right, but already you can see how difficult it is to find the deepest crumple there, right? So you were talking about what is the deepest point on Earth and what is the tallest mountain on Earth. These are the errors from the surface of the Earth. The Earth. If you assume the Earth is a perfect sphere, right? The tallest points and the deepest points, there are actually errors from this the equation people say, mathematicians say, right? So they're errors. Now, but if you look at, for us, these errors seem like mountainous, but they're really mountainous, right? Huge. But if you compare them to the actual size of the Earth, the Earth is actually as smooth as a marble. The error is very low. Right, so that puts the error in perspective and all. I don't know. Yeah, so you can see how already a simple three-dimensional surface has so many different places where the error could have dimples. Very low error here, but you actually miss that if you're looking at all these valleys here that you can get lost, right? So maybe there's a Mariana Trench, right, on the Earth, going right. That's the closest point to the center of the Earth. Yeah. However, we don't have the technology or anything to find that yet. However, we are thinking that in its vicinity is where the lowest point on the Earth is. So we employ these rovers and everything. No, this is all theory. It's story, fiction, right? Right? So we employ all these rovers and everything, and say, well, search here, search here, search here. Not in the Mariana Trench, but search around. And some of these rovers say, well, you know what? Maybe you're right, because here I found a valley. It's the ground is sloping inwards. So maybe that's where the lowest point is, and they'll go in that trench, right? Not Mariana Trench. Some of the trench is not as deep, right? It'll go in there and say, I've found the minimum. I'm going towards the minimum, right? Because they're doing gradient descent. Gradient descent is basically following the slope. Everywhere you have a slope, you're going to go down the slope.
Yeah, gotcha.
That's what we did in parabola. You pick any random point, find the slope, and you have to descend. The gradient tells you which direction you have to go. That's all.
Okay.
And you can do the same thing. You can do the same thing with any number of dimensions, right? You have to do one dimension at a time. Partial. That's that's a multivariable calculus, multivariate calculus. And you do that. It's basically just differentiating, holding all the other things constant, differentiating one. Because you can have a function that is based on a number of different variables. Anything could vary, and if everything could vary at the same time, it's very hard to model the function. So you want to say, what is the rate at which this variable alone behaves when everything else is constant? That is a partial derivative.
Yeah. Quick question. I might get this wrong, so tell me where I'm lacking understanding here. Gradient descent is a way of trying to piece together what your curve or your line or whatever function you've got is.
Yes.
Okay, is it like finding error or?
No. Gradient descent is a way in which you can find the curve that minimizes the error. What you do is take the error, express it as a continuous function of various parameters, The error, make the error a continuous function of the various parameters that define your model. If my model is a parameter, is a parabola, my error is going to be, this minus squared divide by n and so on. Basically, all we're trying to do is express the error as a continuous function of one or more variables. That's all. In the case of our parabola, our error is just a function of one variable, x. But if you have a multi-dimensional surface, like in real life, right? Everything that is erroneous has multiple causes. Yeah.
Yeah.
So each cause says, this cause should not have existed. The right value for gasoline price is here. Okay, but this is an erroneous price. The right price, the right temperature for the day is here, but today is here. And so you have multiple, everyone. So for the perfect day, for the perfect life, you have a lot of parameters here, right? Gasoline must cost, $1 a cent. The temperature must be 64 degrees, right? The humidity. And so you got like a billion parameters that defines your ideal life. But, the life itself is not your ideal life. It's ideal life with errors on multiple axes, right? The gasoline axis has a small error, right? Taking you away from ideality. Yeah. And the temperature today is, like 20 degrees away from ideal. Right, so everything is error. There's lots of errors everywhere.
Gotcha. Still a little bit lost on what gradient descent is. It's
So I'm sorry. So I'm getting there. So all I want to do now is I want to say, because there are errors everywhere, I'm going to define a function, right? That is my total error, which is a function of these individual parameters out there. I want a function of temperature, humidity, gasoline price, all these billion parameters you have, right? I want a function of these billion parameters, which gives me what the error is on every data point. Now that's a continuous function. And if you visualize the curve of that continuous function, it's basically a hyperdimensional surface. It's a surface, and just like regular surfaces, it has ups and downs, it has peaks and valleys, it goes up, down everywhere. But already you saw in a three-dimensional surface like the Earth, it's so hard to find the Mariana Trench when you're close by, and a rover is just following the gradient, meaning it's just calculating the gradient, the slope on a three-dimensional surface. That's what it's doing, right? The rover is calculating the slope where it is. It just got thrown at a random place near the trench, near the Mariana Trench, right? And wherever it fell, it calculated the slope where it is. If the slope is 0, right? It fell on a random spot on the Earth, the rover. Yes, stay in touch with me and tell me if any of this is confusing, right? You threw the rover and say, go to the lowest point, right? This is machine learning. The rover is actually going to do machine learning, right? So you want to find the deepest point on Earth. You took this drone rover and you just tossed it and say, my hunch says that's where the minimum point is. Go and find out. Okay, you tossed it, and the rover just landed in an arbitrary random spot. This is reasonably close to the Mariana Trench, maybe far away. I don't know, right? Landed there, and the place it landed, it's going to measure its slope. Okay, where it lands, measure its slope. Is that possible or not?
Yeah, you could.
Yeah, right.
Yeah.
So now, if the slope is 0, then the drone the robot can immediately signal back to you saying, hey, you know what, I'm already at a minimum point or a maximum point, because the slope is 0. It's not going down, right? Because I'm on flat surface. However, chances are, if it didn't land in one of the minima or maxima, it landed on a slope, and that's the highest probability. Yes.
Yeah.
So when it lands, it can find the gradient at the place it lands. And it finds it's non-zero. Because, it can measure. The rise over the run is, it can measure. You can just dig a shovel and say, well, the rise over run, this is where I am, this is a slope.
Yeah.
Now, if it finds a slope is non-zero where it lands, what can it say about its task? What the task that was assigned to it was find the lowest point on the surface, right? So I threw the rover and it landed somewhere, measured the slope, and it found the slope was not 0. What can it now tell me?
Which direction it should go to start to try and find the minimum point?
Yeah, right. So that's a better thing to say. The first thing it could say is, yes, I've landed in a place and I think it's promising because the ground is sloping, right? It's not flat, the ground is sloping, now I know where to go. Yeah. Now, because the ground is sloping, it can make small adjustments to its position in the direction of the slope. Now, the risk is if it makes huge adjustments, It might actually skip this and go onto that side, right? So it's got to
Yeah.
make small adjustments and slowly march and say, well, I did the small adjustment every time I ended in a place that had slope, and slope slowly started getting slower and slower. And at this point now, the slope is not getting, is not changing. It's almost zero now, right? And that is the lowest point that robot could find. Do you agree or not?
Yeah.
So it has a systematic iterative way of finding the minimum from the place of launch.
Okay. So gradient descent is a method of trying to find the like minimum error and max error, or the lowest down you could go, and so the bounds of where your error is.
Yes, gradient descent is, in fact, it's not even a machine learning term, right? It's been used by statisticians, mathematicians for ages, right? It's used in machine learning recently. It's just a way of minimizing a quantity on a surface when you cannot do it, analytically. You could just take measurements, and the measurements will tell you which direction you need to go. Now, and when you find the direction you need to go, the other important factor is how big your step should be, right? So like I said before, if you make huge leaps, you could pass over the minimum and land on the other side. And you could keep doing that for infinite time, back and forth, right? Oscillate. You'd never find the minimum. You just keep jumping from here, adjusting back like a pendulum, right? You never settle in the middle. So this step here, going from one measurement to the next, is called the learning rate. The learning rate or the learning step. Right?
Okay.
Now in machine learning, one of the things that experts will eventually get a good intuition for is what the learning rate should be. Because if the learning rate is really, really small, you're going to take really tiny steps, and it'll take you a long time to get to the minimum. Yes?
Gotcha. Yeah.
But if you take a very large learning step, you have the risk of missing the minimum altogether and just oscillating from side to side.
Yeah.
So you got to we develop really good intuition for what would be the best learning rate for this type of problem. And that will only come after ages of marinating in the data. Okay, I tell you this, right? I've seen so many. You have to marinate in the data so much that the surface, this hypersurface, essentially materializes in your dream, right? You can actually visualize that and get an intuition for what it looks like and what kind of movement is required to go towards the minimum, or if the minimum exists at all. Or many times you don't know if the minimum exists. You'll say, I'm going to take my chances and just go, I'm going to throw 1,000 spider bots into that surface, right? Each one will search for a minimum where it's thrown, right? And I'll take the minimum of those guys.
Yeah.
That's the least point, right? Even then, the thing that we could say is that we just found a contender. We don't know what the real surface is. We just found a contender. The minimum, this is the minimum surface, minimum error surface, right? We don't know if it's a real surface. So in our, what we can do is, well, you know what? If you generate like a million points like that with a random noise added in, right? And then don't look at the data, don't look at the generating polynomial, or you just take a line where you don't have to be a parabola anymore, a line with errors on both sides. So and you say and your task is to find out what the actual line is. What you can do is essentially try and say, well, I'm going to add up all the errors, add up all the mean squared errors, right? No, the mean squared error is already added in average, right? So I'm going to average, and then I'm going to apply some very basic calculus. Unfortunately, I've forgotten, but if we derive it from. Do you have an iPad or something? Or share screen?
I do not.
Never mind. Okay, this is you'll find it on my. Maybe next time I'll be prepared, right? Next time I can actually draw it. So it's basically very simple math. Okay, it's not math in college level and all. It's basically math that you're doing in high school and college, first years. All we're trying to do essentially is simple.
I am in college.
Oh yeah, even then, right? You don't need college level math for this.
Gotcha.
Right? It's just high school. Yeah. So differentiation. You just need to say this is the error and this is the shape of the curve, and I'm going to differentiate it, set it to 0 so that I can find the value of this parameter that minimizes the overall error. And you've solved maximum minimum problems in in high school, exactly like that.
Yeah.
And that is how you identify the line. But of course, first of all, if you say it's a line, it's easier for you because there's fewer parameters to calculate. You only have to calculate ax plus b. A and b are the only two parameters. Yeah. If you say it's a line. If you say it's a parabola, there's three, ax squared plus bx plus c. Three parameters you got to calculate now. So three parameters could be responsible for your error. With the line, only two parameters could be responsible for the error. Right? Now you can go to more and more complex surfaces, and you have more and more variables in there.
Yes.
Yes. And so you can already see that, the more variables you have, the more complex your error surface will be. With a line, the error surface is so small that you can actually visualize it, differentiate it and everything. You can do this, but you just perfect the technique with lines and then, try and parabola, and then it'll work on any hyperdimensional surface, just like it works on lines, except that, you're never sure if you're getting the actual theory or not, right? The actual, you're just getting the thing that minimizes the error. Like, today, we don't know. Einstein's theory minimizes the error in our observations, but we don't know if it's correct. Yes, it's better than Newton's theory. We know it's better than Newton's theory because the error between Einstein's theory and our observations is lower than the error between Newton's theory and the observations. Right, but we don't know if Einstein's theory is the best. Right, maybe someone else will say, here's a grand unified theory which gives you zero error. Technically, I don't know if you get zero error. It's an even lower error than Einstein's theory. Right, so we'll go to that. We don't know what the truth is in that case. But with a line, it's very simple. So that's why I said, as homework for you, right? Just generate the line. Generate the line. Actually, don't generate the line. Ask your sister or brother or someone in your family to come up with an equation for a line. Just choose two random numbers, a and b, ax plus b. Yeah. Now do that noise thing. Do that noise thing. Add bigger noise. Okay. Don't make it 0 and 1. Add, make the noise wider. Okay. Like add 1 or 2 on this side, so that you look at the points, it doesn't look like a line at all. It looks like that. Yeah. Right now, forget the two numbers that your sister picked. All right, your challenge now is to identify those two numbers from just the points, which has noise added. Each point now has noise added to it, just to the y, right? fx plus noise. Each point now has noise added to it. Now your challenge is to figure out what the line is just from these points, and you do that by saying, right, I'm going to guess that point is ax plus b. If the point, if the line is ax plus b, right, then I can calculate the perpendicular distance from this point to this line in terms of a and b. Yes, now a and b will become variables now, because a and b could be anything. Different values of a and b give you different lines. Yeah. So you could say now a and b are variables because I want to find what a and b to use for my line. So now, so I'm going to make a and b my variables, and so the distance from the point, the perpendicular distance from the point to my line, can now be calculated as a function of a and b. Yes or no?
Yes.
Now, you can do the same thing with every point.
Gotcha. Yeah.
Now you can also square every one of those every one of those distances. Every one of the perpendicular distances can be squared, so everything is always now positive.
Yeah.
You can add them all up and take the mean, so you got the mean squared error of all the points over that line.
Yeah.
So now your challenge is to identify that line, and by taking the error, which is a function of a and b.
Yeah. Okay.
And so
Gotcha.
Say,
I could do that.
Yeah. Sorry.
Yeah. I said I can go for something like that. If I was to do that same sort of thing through gradient descent, from what you said, the way that works,
that's essentially what you'll be doing. You'll just be doing essentially gradient descent, because you'll be setting the derivative to 0, right, and solving for the derivative. And that's essentially what you're going to be doing. Oh, actually, no, because you're doing because you're taking the derivative and setting to 0, it's an analytical way to find out. It's not gradient descent. I'm sorry, I'll take that back. Okay, you're just getting to the a and b through analytical means. Gradient descent is when you don't know what you want to. Gradient descent is when you actually calculate the slope. You take the derivative, plug in the values at that point, and then calculate the value of the slope. And if the value of the slope that you calculated, because you've got the equation of the curve, yeah? If you've got the equation of the curve for some value of a and b, you're going to assume random values of a and b, right? You're going to assume a random value for a and b first, and then say, but my line is going to be 3x plus 7, y equals 3x plus 7. You don't know if it's 3x plus 7. It could be anything. We just postulate a random line, yeah? 3x plus 7. So for that 3x plus 7, you can You can essentially, basically you can calculate the error of all of this, some of the data points, and then you're going to differentiate and set to 0, so that I lost my train of thought here. I don't know what I was trying to explain. I'm sorry, Andrew. But essentially, what you're trying to do, and tell me if you're confused. Maybe that will bring me back to what I was trying to say. Is essentially what you're trying to do here is you got a whole bunch of data points, and you want to calculate the errors as a function of the coefficients of the line, and then you can differentiate that, set it to 0, and solve for the coefficients, and say if the coefficients were this, then the error will be 0.
Okay.
Or the error will be minimum.
Yeah, gotcha.
We can actually do an example if you want. It just needs a little bit of math, and we need an iPad ideally. I don't know if we can do it here. Maybe next time we meet, I'll think up a better way to do that. Well, anyway, that was only one of the experiments I wanted to run past you, because there's another easier one you can do, right? It's the easier one that you may actually be interested in. It doesn't involve grading the sand and all that thing, right? It's much simpler. Now, this is something that one of my 2C students actually did and displayed at the STEM Center. It's called a STEM Day, okay? It's called STEM Annual Day or STEM Day, where the students can bring their projects. So here, and this is something that you should try and do, right? So suppose I give you a random passage in English. Just type something and give it to you. And your challenge is to look at that and say, well, that looks like it was written by Shakespeare or by Byron or by Charles Dickens or Mark Twain, right? So that is machine learning. And that is a huge field of machine learning called language modeling, okay? That's a huge field. It is usually, it's very interesting. There's lots of things you can do there.
That's the other one.
Do you want to try something on that that front? I can show you. Hey, Peter. There's Peter. So he comes by and gets cookies from time to time.
Is that a squirrel?
Yeah. No.
That's fun. Yeah, we had a couple in our yard too that used to come in sometimes, but we got this dog who we love her, but
he chases them.
Yeah, she's super excited about everything, and so the squirrels stopped coming, and we stopped putting out food because we didn't want to lead them into the yard so that they'd get chased away by her.
That is so fun. So fun. I love watching them. They do some crazy antics out there. Okay, so anyway, so do you want, and that is an experiment you can actually easily try to, and it'll be very, I don't know if this may be like, biscuit dry for some people, this particular line, and linear regression. It's basically linear regression. What we did here is just linear regression. We're trying to find the line that, and that is part of machine learning, believe it, right? In fact, that is the first part of machine learning. Before you get into more sophisticated aspects, that is something that do. And so even for before we leave this topic altogether, these neural networks, essentially the way they work is that they receive lots of inputs. Each unit in a neural network receives lots of inputs. They'll sum them all up, and if the sum is greater than some threshold, some firing threshold, it'll blast a signal out, which means that in our brain, lots of synapses touching all these axons and neurons and so on and so forth, right? So essentially, you can imagine it like this. Each head unit will receive some neurotransmitters or chemicals from a whole bunch of connections, right? So it'll start accumulating in here. When it, like a capacitor, right? When the amount of chemicals in here increases past a certain threshold, something in here will burst, and that'll output. So that's essentially what you can say is your fundamental building block of a neural network, right? It's basically modeled after a human brain. That's why it's called neural network. So a neural net is basically a unit, and you can build these in C++ easily. I can show in 2C. Essentially, you have a class, and it takes multiple inputs, right? add up all those inputs and compare them to some value. If sum greater than 10, right, then output equals 1, right? Otherwise, output equals 0. That's all. Now, if you think about it, that is very hard to model mathematically. And so if that's all a neural network, if that's all a neural node did, we would be in deep waters. There wouldn't be any machine learning. There wouldn't be deep nets and all, right? So the reason why neural networks are so big these days is because we discovered a way in which they can be mathematically manipulated and pushed in directions we want. And that is because previously what we had was a step waveform, right? So we had 0 voltage or 0 current, and the threshold was reached, and then all of a sudden, bam, it goes to 1 volts, right? So there's a step function here, like that, right? No threshold, the unit is not firing. Here, the unit is firing, right? Threshold was breached, and the unit is firing. So between here and here, some magic happened, bam, like that. Yeah. So that is very hard. That is very hard to model mathematically because that place is not differentiable. Yes?
Yeah, gotcha.
Right. So now what we did essentially was there's a mathematical curve called a sigmoid, right? If you go to a Chrome window and just in fact, you can go to go to Desmos. I'll show you. Go to Desmos. So type what is a sigmoid?
Get rid of these.
All right, so get rid of all of them, including y equals x squared. Type y equals 1 over 1 plus e to the negative x. 1 plus e to the negative x. I think. Hang on. Yeah, e to the negative x.
X.
Oh yeah. Okay. All right. Good. Now zoom into the middle part. All right. You see how, right? Now, if you zoom out all the way, right? No, not yeah. All right, that's enough, right? You'll see that this is actually infinitely long. It goes all the way from negative infinity to positive infinity. Yes.
Yeah.
However, for the bulk of its life on the negative side, it is 0.
Oh yeah.
Right, and for the bulk of its life on the positive side, it's 0.5.
Yeah.
Is it? Yeah, it's 0.5. I don't know, somewhere there. Okay, right. But there, in between, a transition happens. Now you can liken that to the neuron accumulating neurotransmitters or whatever it is, right? The threshold, it's summing up all the values coming in, but the threshold hasn't fired, and when it fires, it goes off to that 0.5 level. Until so here it's not firing that. Now this is you can model that because that what we just described. There's a continuous curve. You can differentiate it. Yeah, if you can differentiate that, you can add up many of those. You can multiply them. You can add, you can make, right. You can still differentiate that. In some combination of that is still going to be a differentiable function. So if you make a surface made up of these curves, that surface will also be differentiable, and then you can apply gradient descent techniques to find the minimum points on that surface. Now, however, one thing we notice here is that this thing here is too gradual. It doesn't look like a computer generated, emission, right? It's a computer. We want step waveforms, right? We want really hard black and white distinctions, no gray areas in computer science. Yes.
Yeah.
So the way we can do that is still keep it continuous and say 1 over 1 plus e to the negative 10x, right? Make that e to the negative 10x. There you go, right? So make it e to the negative, because all you're doing is basically e to the 100x, negative e to the 100x, and negative 100x.
Here we go. Woo!
No, it's not 100x.
I was sorry, I was just making a little fun thing. Give me a second. There we go.
There you go. Yeah, I see. Yeah, there you go. Now it looks almost like a step waveform, right? But it's still differentiable. Because it's a continuous function. You can differentiate it. So which means you can apply a gradient descent, all those techniques we know.
Gotcha.
So if you construct so this curve is got a special name. It is called a sigmoid curve.
Oh, okay.
A sigmoid curve is basically is essentially the core property that makes neural networks tractable and easy to use. Now, if you go to a deep neural net, you have billions and billions of these nodes, right? Each of them have lots and lots of inputs coming in, and their output will go to some other neural node, right? So that node will contain lots and lots of inputs coming from many other nodes. So it's, as you can see, now each one of those will have so many parameters, and so to model those, you'll have to have a hugely hyper-dimensional surface there. Yeah? And you got to basically differentiate that. So the risk of falling into a minimus is very, very high. Local minimus, right? What I mean by a local minima is that the rover that fell on the surface of the Earth near the trench fell in a valley and said, hey, I'm in a valley, which means I'm going towards a minimum. And I went to the valley, and I went to some part in the valley and said, that's the deepest point in the valley, and that should be the deepest point on Earth. However,
it isn't
there's another
necessarily the
place.
deepest point everywhere. Yeah.
Yeah. So that is called a local minimum, right?
Yeah.
So the greatest danger in machine learning with neural nets, especially, is that you'll settle in a local minimum and think that is a global minimum. Because if you think that is a global minimum, you're not going to you're going to stop searching, essentially, right?
Yeah.
So you'll never find the truth, right? The true minimum, and you'll get stuck here in a local minimum, thinking that is the minimum everywhere, because everywhere around you, the ground is sloping upwards.
Gotcha.
So how do you find what? So that is why I said, marinating in the data. And that is why a lot of people, who get into machine learning think, oh, it's easy, I can do this, do this. No, it takes ages of marinating in the data. And also it won't happen if you keep switching fields and still doing machine learning, right? Someone could say, I'm a machine learning expert. I've been doing machine learning for 10 years. First 5 years, maybe in speech recognition, another, something else, many different things. And looking at different data, driving data, autonomous satellite data, and so on. Yeah, okay, maybe they get some intuition, but not as much as a person that marinates in the same data for a long time. Because when you marinate in data for the first year, you may think that there's nothing in this data. I can't get any patterns out of this, right? The second year of the same data, nothing has changed. You will say, right? If you're still in the same company, you'll say, well, last year I thought there was nothing in here, but now I can look at so many peaks and valleys. Yeah. The third year, you'll say, well, you know what? I thought there were lots of peaks and valleys, but there's more, right? And in fact, there's even a pattern to where I can find deeper ones. So that is what makes, 6-figure and 7-figure machine learning engineers. Because otherwise, everybody else will just be a resource kind of person who's just responsible for culling data together, cleaning up the data, performing all the janitorial tasks on the data to make it ready for feeding into the net. But only a person who has real insight and intuition, that person has actually marinated in the data for a long time. They'll actually know, right? Exactly the kinds of configurations and what kinds of, initial weight distributions you should use, so that you don't get thrown, near a valley. You actually get thrown near the Mariana Trench.
Yeah.
So that is what people pay for, right? And when people say, machine learning is lucrative and things like that, it's really, they're talking about the top few people who actually have these insights by investing a lot of time already, right? They invest 10 years maybe, and then come up with these insights, but they make it look like this whole field is now a gold mine for everybody.
Yeah.
Yeah. And that is a risk that students could fall into. That is why you need to be aware of many different places where you could contribute, not just machine learning. You could go into game development, right? So I'm not saying don't go into machine learning. So you could go to game development. So game development also, there's cool things. You can apply machine learning in game development. Yeah.
That's what I'm doing currently.
Because you can say, you're going to play with Adam 475. Adam 475 always uses, a balloon axe after this, or something like that. How do you know? Random person. You only played 5 matches with that person. But you can use machine learning to figure that out, right? So if you build a Fortnite-like game, you can figure that out. And that person playing a game will say, wow, this system is really kick-ass, man. You know what? I pulled a new trick on it, and it immediately knew that I was going to do it, right?
Yeah.
And so you've seen people make these comments, right? In when they play these games? And my son used to say this, the Halo and all used to say, when I used to watch him, he'll say, wow, did you see that move? That could never have been made by AI. Someone is playing there or something like that. But it's really cool.
I've seen a lot of stuff for can't say a word. Super Smash Bros. Ultimate. They have some crazy CPUs.
Yeah. Oh, it uses a lot of CPU?
Yeah, well, no, the ones that they
you mean by CPU? You mean the characters? NPCs,
yes.
You mean the NPCs?
Yeah. The other ones you can get to fight you. They're surprisingly clever when you put them up at high levels. They did really good on those.
Wow. Yeah, that's really interesting. Yeah, it's just a matter of time. Because at some point AI will also start saying, well, you know what? I've exhausted all. The limit of humanity. I've reached the limit of humanity, meaning that I can easily solve anything humanity throws at me in my sleep. right?
Yeah.
Because the AI power is so much. So I need to find out solutions that even humans cannot figure out. So I need to look at this error surface in ways that humanity has not looked at. So I can discover points and patterns that people haven't seen.
Gotcha.
But I can do because I have so much more bandwidth, because AI has so much more bandwidth than humans, right? We're here for a puny 100 years, right? But 100 years for an AI system is like trillion years for humans, because they go so fast. Yes.
Yeah. Yeah.
So basically it has a luxury of so you can do a lot of things. So for students, I think, especially in college, it is easy to get enamored by these lucrative fields like AI, machine learning, all these things, right? And say, I
I
want to
just
go
want to learn it
down that
because it
path.
sounds fun.
Yeah. But but I'm saying there's fun everywhere. Game development also has a lot of fun, right? But you shouldn't go to game development because I said so. But I'm saying if you
Well,
learn C++
that's what
and
I'm
the
already
underlying
going to.
techniques. Hmm?
I'm already trying to go into a game development. There we go.
Oh wow! Oh, that's nice. Are you using Unreal or Unity or something like that?
I've used them a few times in the past, and I learned I was kind of bad at them, which is one of my hopes behind taking this class. Because I know Unity works in
You mean
C
CS2A?
sharp. Yes, CS2A, and I'm going to take it all the way to C, and possibly a few other classes over that. Because after these 2 years, I'm going to go into Santa Cruz because they've got really good courses for that. And
For
my
game
hope
development?
is, yeah, my hope is from learning more coding and getting into more in-depth stuff that I haven't gotten into yet. I'll be able to understand some of the stuff that I haven't been able to get with stuff like Unity, and then really start to mess with making my own games.
Yeah, exactly. But by the way, you don't have to learn all of them, right? You don't have to learn Unity and Unreal and that and this. You just have to learn one, and everything else just use a slightly different terminology, but it's exactly the same.
Yeah.
Yeah. And I would say, since you're doing majoring in the C++ track, learn Unreal rather than Unity. Right?
Oh, okay.
It's free. There's like tons and tons of tutorials you can download. They have Unreal University where you have free classes, online classes, everything. And Unreal is easier to work with for C++ programmers because you generate your code visually and with visual arrows connecting here and so on. And then you can just hit this engine to turn that into C++ right in front of your eyes. Bam, like that, it'll turn to C++. Where all of these things that you can't turn to objects.
Does Unreal let you do scripting, or is it just their
visual scripting? It does visual scripting. You can it's better than other. No, yeah, you can actually drag things into place and connect them with arrows like flowcharts. So that level of scripting, you can do visual programming there. And the cool thing is that whatever you do visually can instantaneously be transformed into C++ and vice versa. Bam, bam, like that.
Gotcha.
So it's very nice. I've just been years since I played with the Unreal Engine, but I think that it's easy and and it's worthwhile learning and fun too. So if you're going to do CS2C, maybe I'll just guide you with a project on Unreal. Develop a small game.
That would be fun.
Not now. You after you.
Yeah, once we get there, yeah.
So once you get there, I can guide you with a project on Unreal, and it'll be a real fun game too that you can actually release. I think.
Okay.
Yeah, those are things we can do, and even theoretical computer science is enormous, juicy things that you can sink your teeth into. But the thing really, at the end of the day, is not to drive towards any particular hard goal like machine learning or game development or whatever it is. Just go for the concepts, because the concepts of the nuts and bolts that you'll pick up that you can just use to assemble anything you want in any field you go into. Then once you pick up the concepts really strong, like what is a hash table, what is this, what is that, what is gradient descent, and good on mathematics, because you can start visualizing these surfaces and all, right? Then then no matter what field you get into, even whether it's finance, whatever it is, you'll automatically bring all these tools that you already have at your disposal, right? And you'll be off to a running start. And then you'll be talking to the pros in your place of hire, day two. Yeah. And talking one-on-one with them. Cool stuff. Instead of just saying, what do you need me to do, sir? Right? I'll do that for you. Because that's how all the newbies do the first year, right? First year, they're always so obedient and say, all right, I'll do whatever you tell me to do, right? And you don't have to be like that. Day two or week two, you can just start, going out to have coffee with all the top people and saying, hey, that's a really cool idea, let's try it out. And you try it out over lunch and say, I tried it out, that was a really cool idea, or this doesn't work because of this. All these things, those are things that people value, right? Many people I find, especially in the Bay Area, and maybe I'm wrong, are enamored with this word called manager, right? And management. In fact, they're so enamored that they even go for words, jobs that have manager in the job title, like product manager, right? But a product manager is not a manager at all. This is trying to manage a product, not humans. Managing humans is harder, right? However, even managing humans, there are people who say, I have 50 people under me, 100 people under me. And that's all stupid nonsense, right? None of that really matters, because managers are not leaders. What you want to be a leader, not a manager, because even a manager is not executing their own vision. They're getting a vision that's handed down to them from the king, right? And say, well, the king is going to have my ass if you don't do this. So I'm going to whip you until you do it for me, right? That's not a manager. That's not a leader. This is a manager. Manager is someone intermediate who just gets things done, right? So what you want to be is a leader. And a leader needs to be able to think, right? And say, I'm not interested in just managing stuff, because it's the same as just individual contributor. I just want to be doing cool stuff. When you're doing cool stuff, what happens is that you get cool ideas. And ideas will only come to leaders, because they'll say, this is really cool, everybody should do it. And then everybody will say, even if you don't tell them to do it, they'll be doing it because it's cool. Because you got buy-in already. So getting buy-in from other people without having to coerce them or even convince them that they should do it, that is the mark of a leader, right? Because they'll say, this is the idea, and all the other people will automatically be sold.
Yeah, gotcha.
Yeah, so that is, and I think that is, and you get that only by drilling really, really deep down into the concept. So meaning that you have a garage full of tools, and you know how to use every single tool, right? That is a mechanic you want to take a car to, right? Not someone who says, yeah, you got my car, let me pick up this manual for 2020 Volvo and see what needs to get done. All right. So no, yeah, all right. But someone who says, yeah, I've done this like a million times, I know what to do, right? I do it in my sleep. That's a really cool guy, right? So they know what to do. So that is the trick. And in order to be, and they'd be able to say, you know what? Usually millions of people will repair that like this. But I know if you do it like that, it doesn't work. So for your case, I think this special solution will work much better. So we'll do that. Okay. Only someone who knows everything inside out can say that.
Okay.
Yeah. And I think that is why I say, when we're in college, don't get misled by all these other people in the Bay Area saying, you got to do this, you got to do that, you got to get into machine learning, or just say, I want to learn the concepts, because now you got the luxury. You got your mom and dad and everybody taking care of you. You say, all I need to do now is just pick up all the concepts, or everything. I need to learn to use every single thing out there, so that when I'm out there on my own, I can just put everything to use. So anyway, so one thing you can do is as another project, instead of the as a line fitting, is trying to figure out by language modeling. Language modeling is huge, right? What a particular piece of text sounds like. And that is also very crucial in speaker identification, right? So if I talk to Google and say, hey, Google, what is my bank balance, right? Google could actually give me the right answer, provided it could identify my speech and tell with 100% certainty that it was me.
Yeah.
Right? Otherwise, it'll say, no, unless I authenticate you, I can't do that. Yeah. So, and so there's a lot of different cues in what I say that help the other party understand who the words are coming from, right? Whether it's from me or from my friend or someone else, they'll be able to tell just by listening to the words that we speak, as also to the voice and timbre and everything like that, right? But suppose all the voice and everything was hidden away, and we all had to write, communicate by writing. Will the other person still be able to see the writing and say, this letter was written by Andrew, this letter was written by Nemo, right? It's possible to make an educated guess, not with 100% certainty, but with a very high degree of certainty, better than average, using machine learning. And you do that using language modeling, right? And if you're getting tired, we don't have to do this today, we can do it next class, but I'd still like to leave this as homework for you. Is essentially with language modeling, all you're going to do,
definitely,
you can start really, really simple. Start really, really simple, and basically just count the frequencies of words used by all the people, right? So Nemo gives you a 1 hour spiel of some speech he's prepared for English class, right? Adam does the same thing, right? Ashley does the same thing. So you got all these 15,000 words from each of these people. right? Now some random person says, here's a snippet. Tell me which of these people spoke it. How do you find out? Right? One way is to do is simply say, this in the snippet, the word metamorphize, right? Occurs 5 times in the snippet you gave me. But of all these 3 people, only Ashley used metamorphize 2 times. The other 2 people didn't even use metamorphize. So the snippet is very likely to have been spoken by Ashley. Would that be a reasonable conclusion?
Yeah, based off your data.
Yeah, okay. Yeah, right? Well, it's very weak, but at the same time, it's the strongest you can get because it's only based on one word. It's one word, right? But it's still the strongest you can get. Now, technically, you can do a lot better than that. You can say it's not only metamorphize. Metamorphize, Ashley has a 50% chance of using, Adam has 25, Nemo has 25, right? Let's take another word, Epicurean, right? Epicurean, that's also there. Ashley has a 70% chance of using that. These people have 20%, 30%, right? So for every word, you calculate the probabilities that different people would have said it. And then you can calculate the total probability that the entire snippet was said by Ashley, the entire snippet was said by this person, or Adam, or Nemo, or so on and so forth. Yes or no?
Yeah, you're getting closer.
Getting closer, right?
Yeah.
Now, based on the total probabilities, can I not select the most probable of the 3 and say that is the person most likely to have spoken this passage?
Yeah, can do it.
Okay, that is called maximum likelihood inference. Okay, it's called maximum likelihood inference. This is another very common technique we use in machine learning. Maximum likelihood is just to find the most likely person or most likely model to have emitted the observation. That's all. Right?
Gotcha.
And in order to do that, it's very simple. All you have to do is take the text that Ashley has spoken, maybe 1 million words of her text, right? And just count all the words, right? The word "the" occurs 75,000 times. The word, and so on and so forth, right? You have a count of all of the words. Now you have a count of all of the words. You can also calculate the probability of each of these words, because the probability that the word was spoken by Ashley is basically the count, the number of times divided by the total number of words, the total count of all of the words. Yes?
Yeah.
So you have the probability. Yeah, you can calculate the probability of each word. Now you can calculate the probability of the entire corpus, because it's the product of the individual probabilities. Now, however, each probability is going to be so tiny, yes? Because, you're talking about, the occurred 50 times in a corpus that is 5 million, right?
Yeah.
So the probability of the is 50 divided by 5 million, which is a very small number, yes?
Yeah.
So the probability of each word is going to be very small. So if you multiply all of these small probabilities, you're going to get even smaller numbers. 0.5 times 0.5 is 0.25.
Yeah.
Right? So as you multiply these probabilities, the numbers get smaller and smaller. So it's very hard to use even double precision arithmetic, even in C++, to get to the smallness of these values. And so what we'll do in that case is, instead of using the small values raw like that, we'll take the log of those values, right? And use them instead of using the values. So when you take the log, big numbers get flattened into small numbers. Yes?
Yeah.
10 to the minus 100, 10 to the minus 100, 100 just becomes minus 100. Log to the base 10. Right? Now, instead of just multiplying the probabilities, you can add the logs of the probabilities.
Yeah.
Because, A times B, log of A times B is the same as log A plus log B.
Yeah, I gotcha. So
you can add the logs of the probabilities. Now, that won't result in underflow or overflow, because all the numbers will be within range, like 100, 200, and so on. You can add them all up, and you get the logs of the probabilities. Now, in order to pick the most likely one, the one with the least probability, I can also pick the one with the least log of the probability, because log is a monotonically increasing function in X, right? If X is smaller, log is also got to be smaller, right? So it's the same. It follows the same pattern. So instead of minimizing X, I can minimize log X.
Yeah.
So instead of picking the least, the most, or the the least likely, the most likely person to have spoken it, I'll pick the person who has the most log likelihood of speaking it, which number is much easier. So that is basically instead of using likelihood directly, you're using log likelihood. That's all. So when people say you got to operate in log space, that's all they mean. Say they're saying the real space is too sparse and far between. Let's just crunch it all together and operate in log space so that all the numbers are within viewing distance.
Okay.
So that's like we've talked about a lot of concepts, little concepts in machine learning, but they all touch in on different places where you learn about machine learning, and you don't have to learn them as part of machine learning because these are all general tools, right? Mathematicians, statisticians, they've been using this for hundreds of years. So once you pick up these things, and when people say I'm going to learn machine learning, and in this course I'm going to learn about reducing log error and so on and so forth, that is a wrong approach. They will not learn it. Okay, reducing the log error is just a general concept. You should learn it independent of machine learning. Then inside of machine learning, you're going to bring it to bear.
Yeah.
And so that's why I say, if you just focus on the concepts, when you go to machine learning, you'll see the professor saying, well, we'll just minimize the log error there. Right?
Okay.
And things like that. And that's what they're saying. And lots of people I know, as soon as they say we want to take the derivative and set the log error to 0, they'll just switch off their minds at that point. Okay, because even thinking in log space is too much for them. Derivative of the log, again, they'll say, all right, I'll read the book later on, or watch a video, or YouTube somewhere, right? And that's a dangerous thing to do in class. Okay, in class, and especially in 2B and 2C advanced classes, the worst thing students can do is to say, when a lecture is going on, if there's a point I don't understand, well, I'm not going to trouble other people and the rest of the students. I'm just going to make a note and I'll watch YouTube or read up and come back and understand that later. This is the worst possible thing a student can do, because by saying I'm going to defer this to later, you're automatically deferring everything that comes after that too, because you're not going to be focused anymore on this because you've lost here. You're going to say I'll pick up from here when I watch the YouTube video, and it is so much harder to pick up everything on your own. So it's better to go to class already knowing this, so that when you can just keep in step. Always being in step with the class is much easier for the student than going out of step and then coming back to step later on. And a lot of students, unfortunately, are seeming to do the harder part, saying, well, I'm not going to do the easy part of paying attention in class. I'll pick it up later, meaning I'll do the hard work rather than the easy work. And so all of this ties in together, right? And you don't have to do that, because if you just review the material one day before class, not my class, any class, you'll just come across a few concepts that will be blockers. Okay, it's not the entire class is not going to be blocker. There's going to be a few concepts, and the problem is these few concepts will basically throw off the student from progressing past to stuff that they could potentially have known easily, right? And so you just need to go one day before and say, hey, that concept. That's all, 2 or 3 only, and say, if once I know these concepts, I can stay in step with the lecture, and that is the easy part. That's all right. Anyway, so what you can do is, well, you can. What time is it now? Holy cow, it's 3 o'clock already.
That was actually that was something I was going to mention. It's been fun. Thank you. I've learned a lot so far. Your task that you told me about, the trying to write something that can figure out what exactly the line is based off of points with a certain amount of error in between them, calculating all of that. I want to look more into that. Also, language processing. Definitely going to look more into that myself.
Yeah, totally.
Yeah, and thank you.
You should
Sadly,
do that.
I do think I want to cut stuff short. If you have a few more things to say, that's great. But I forgot to have lunch, so I probably need to go do that.
Don't worry. Well, don't worry. Okay, we can cut it. We can cut the lecture now. It's not really a lecture; it's just a meeting. And it's already on YouTube. You can watch it later if you want. And if you want to follow up on any of the ideas that I've mentioned, like let's implement the language thing together on screen. Yeah, something like that. We can do it in another class. Just send me an email saying, or can we do another Zoom where we can implement that, right? And so on and so forth. We can do all that. I can help you with all these things. Okay. So cool. It's going to be fun, especially you're in 2C, so we'll have fun.
Awesome. Cool. Thank you.
Best of luck with everything. And I haven't done the grades yet. I'll do it later today.
Yeah.
But I'm pretty sure you've done. You got up to quest 9, so I think you've done well.
Awesome. Thanks. Yeah, no, I didn't do brilliant on the tests, either the midterm or the final. Those always threw me for a loop. But I think the quests are fine. I got a
Great,
bit over
great.
180.
But, you know, when you're doing 2B, a lot of 2A will automatically fall into place. So,
Okay. All right. Appreciate it.
all right.
Um,
Best of luck with everything, and you know, and send me an email if you want another meeting. Okay.
Thank you. All right. Have a
All
good
right.
day.
Bye.